Thank you. So, we are looking at Hope's experiment. Which is actually an experiment that demonstrates anomalous expansion of water. It doesn't prove it. It doesn't prove it so much by showing that this is what happens, but it demonstrates it, and you can understand it only if you analyze what you are watching. Okay. So for that we require to look at the graph of temperature variation against volume for water between the range of 10 degrees Celsius to 0 degrees Celsius. We know that the volume of water drops as it does for any other substance, comes to a minimum of 4 degrees Celsius, minimum at 4 degrees Celsius, and at that point of time, instead of decreasing further, the volume increases. You would expect for most solutions that the volume will continue declining like that, but that doesn't happen, it increases. That's what is called as anomalous expansion of water. But to understand Hope's experiment, you need a companion graph. So the companion graph, as I call it, would be temperature versus density. And the temperature versus density would be the mirror of the temperature versus volume. So that's why I drew it up and down. From 10 degrees to 0 degrees Celsius, the density of water will increase owing to the fact that the number of particles remain the same but the volume is decreasing, and becomes a maximum at 4 degrees Celsius because that's when the minimum volume takes place. And then because it increases in volume after that, the density decreases. Of course, the change is not as dramatic as shown in these graphs, but that is to give you a picture of what's happening. Now let's come to the apparatus. Okay, so Hope's apparatus is something like a jar. Let's quickly wind up that. And right at the center of this jar, you have a sort of skirt, so to say. So it's like a container. So you can't see this obviously. Okay, and that container is packed with ice that is melted. So you have ice placed inside this. And of course, you can, as the ice melts off, you have to keep replacing the ice inside that. So the whole thing is filled with ice. Now you fill this container with water, the jar with water. Okay, so this is your jar. This I call it the skirt. I am calling it this, okay? Skirt with ice and salt mixed. Actually, that's the original experiment. So maintain it at 0 degrees Celsius, and then you go inside this water. So here you have water at room temperature, they say, and then somewhat paradoxically stated as 12 degrees Celsius. Okay, room temperature is more like 25 degrees Celsius, but they are calling it 12 degrees Celsius. But basically, it's above the temperature of the ice that you have over here. Ice, of course, is going to be at 0 degrees Celsius. So this part is at 0 degrees Celsius. Okay, now let's talk about what happens. Of course, I forgot. You would have placed two thermometers. Okay, one over here. I mean, it's slightly different in your textbook. I think the thermometer goes on that side. I suppose nobody wants an explanation for why that is so. I have written stuff on that side, so I have to answer on this. You are being recorded, so you have to speak loudly. You tell me.
Sir, also could you move the camera towards the right?
Towards that side?
Yeah.
I need to show the graphs also. There isn't much, I have just written some stuff down. Okay, that's what I have written there. Right?
Okay. Yeah.
I need the graph on the picture, otherwise it won't make sense. Okay, so initially to start with, so you'll have to work with me on this together. Okay, so think through this with me. So this is thermometer T1. Am I right? Even in the textbooks, I don't know.
Yeah, sir.
We're changing it. Actually, you can put whatever you want, but they are calling this T1 and T2. So this thermometer is T1 and the temperature it reads is T1, and this thermometer is the one that measures T2. So when you pour the water in at 12 degrees Celsius, what is going to be the temperature required in the thermometer? 12 degrees Celsius. So to start off with, both thermometers are going to show 12 degrees Celsius. Okay, so maybe I shouldn't write it there, but that's just the beginning. So T1, T2. If I take a table of T1 values versus T2 values against the time. So now what you're going to do is you keep a stopwatch, and let's say it's cooling down. So let's say once in a minute or so, you note down the temperatures both for T1 and T2. So this is what you're going to observe. Then we will discuss why you are observing what you are observing. So this is the time in minutes. So minute 1, minute 2, we should always start with 0. 1, 2, 3, 4, so on. So you will first see the value for T1 will be 12 degrees Celsius. So this is in degrees Celsius, this is also in degrees Celsius. No confusion about it. Time T is equal to 0 minutes, both are 12. Then you will find that 1 minute later T1 is still 12, this has gone down to 10. 12, maybe 8, maybe 11.5, something's got to give 6, then again 12, 4, then you carry on. It's not going to happen this fast. In 5 minutes, 6 minutes, 7 minutes, you're not going to observe this, but this is some kind of a time frame. Okay, so maybe it will become 3 here, it's still at 12, then it will become 1, still at 12, and then this will become 0, and this will be at 11. So what is happening? The water which is at the top part, okay, that's not being affected by the ice. Whereas the water at the lower part, that is being affected by the temperature of ice, and that temperature you see dropping. I made a big mistake. I shouldn't have dropped those things. These don't matter, sorry. We'll stop at 4. We'll stop at 4. Okay? And then what you are going to see is after this, this temperature will remain at 4. And this temperature will start to drop. 10, 7, 5, 3, 6. Okay, so the change is taking place in the top in this phase, and the change is taking place at the bottom in this phase. So now the question is, why does this occur? Okay, so that's what we have to understand. Any questions at this point of time?
No, sir.
Yes. We need a moment to note things down.
So,
Okay. So this is what the observation is. So initial part of it, the lower temperature is registering a change in temperature. Okay. But it's not going all the way down to 0. It's going down to 4 degrees Celsius and then stopping there. So wink, wink, nudge, nudge. Okay. And then the upper, all the while that is happening, the thermometer at the top, nothing happening, nothing much happening. You may notice some changes, but nothing much happening. There's always thermal agitation going on. So there may be some minor changes registered, but no steady drop. When this reaches 4 degrees Celsius, then you start to see that there is a change in this thermometer. Okay, that temperature drops. In fact, if you cool it sufficiently, this can go down up to 0 degrees Celsius and you'll actually see ice being formed at the top. So, what is the explanation? Why does this happen? Now, we need this graph. We need this graph to understand what is going on. So, what was happening? Initially, the water was at 12 degrees Celsius, both places. Right? Now, this ice is cooling the water in this region. Right? In this region, the water that is there inside the jar, that's being cooled down. So when it's cooled down, what is going to happen to the density of that water over there? Yeah. The density will increase. So the water over there has got higher density. Okay, higher density compared to what? Compared to the water over here and also compared to the water over here. So in comparison to that, this has lower density and so does this. Okay, since this water has higher density, now what movement is going to start to take place? That is the important thing, right? What will happen? The higher density water starts to go down. Why? Because it's just simply higher density. The we have studied this, right? Objects with greater density go down and objects with lower density come up. Oil and water. So what is going to happen is the higher density cold water is going to go down, okay, and the lower density relatively warmer water is going to go up. Okay, so there's going to be a cycle that's going to get set up because when the lower density water goes up, it's going to get cooled down again. Again, it's going to get higher density, it's going to come down, and this cycle keeps happening. This process is what is called as a convection current. Okay, so because of temperature variations, the density changes, and when the density changes, there is a cycle that is set up. Okay, the same thing happens in the Earth's interior when the hotter substance which is closer to the core, the things that are higher above warms up, cools down, gets higher density, then it goes down. So actually there is a convection current which is set up in the Earth's crust or below the Earth's crust, and that is what causes plate tectonics, the movement of the continental plates. So this convection current business is deep; it's like huge. But here we can see it in Hope's apparatus also. So naturally, when the convection currents are happening over here, slowly the water over here is dropping in its temperature, right? Because this is getting cooled down because of the convection current. That is why T2 you observe the temperature dropping steadily. At the same time, nothing is going to happen to this because this is lower density in comparison to the cooled water over here. There is no chance that the higher density water can go up or the lower density water can come down. So this is left unaffected. Nothing happens over there. That's why you will notice that the temperature does not change in the first place. Okay, so that is the explanation for this part. This is done now. We understand why T2 changes, and we also understand why T1 does not change. Do you have a question? Anybody has a question in the class?
No, sir.
No? We'll move on then. Okay. Now we come to the second phase. Okay, and why is the phase? This is not a phase change as in from solid liquid to gas, but it's like this part stops and then this part begins. So let's see why. Now this convection current has run its course, okay, and all the water over here is at 4 degrees Celsius. Okay, water at 4 degrees Celsius has the maximum density that is possible, right? So now what happens is that there is no possibility for any convection currents to happen over here. So this temperature change stops. It goes to 4 and then it remains at 4 throughout. However, what is happening at the top? Now this is high density Okay, this is low density, it's cooling over here. So again, convection currents are not possible. I think in the textbook by mistake they mentioned that convection currents will be set up over here. Convection currents cannot be set up over here. What will simply happen is that the ice will start cooling down the water from bottom to top. So the temperature will just simply decrease from this point onwards. So here it was 12 degrees Celsius. So what will start happening is water over here may be at 10 degrees Celsius. Here it is still at 12 degrees Celsius. And then after some time this will become 8 degrees Celsius. So the water which is slightly above it may be at 10 degrees Celsius. Right? So the cooling will spread from the lower part to the upper part. Because the cooling has to absorb energy from somewhere, right? So it's going to take TKE away from the water which is there at this portion. Why? Because you are continuously replacing ice. When the ice melts, you put fresh ice. So you maintain the belt over here at 0 degrees Celsius. So then what it's going to do is it's going to start dropping the temperature where the thermometer is. If you keep the thermometer closer over here, you will actually see the effect faster. Keep it over here, it will be slow. If you keep it right at the top over here, it will be even slower. But eventually, all of the water over here is going to equalize with the temperature of the ice. So this will go down to 0 degrees Celsius and it may even solidify if you leave it for sufficient period of time. So that's what this part of it represents. Okay? So how does this show the anomalous expansion of ice? It is confirming with the fact that the highest density of ice occurs, water occurs at 4 degrees Celsius. For otherwise, how can this phenomenon take place? Okay, and the other thing is that in terms of application of the phenomenon, we can talk about one or two things. But yeah, you had a question. Why doesn't it continue to cool? Because it's not going to. I mean, I suppose that some part over here, just simply because of exposure to the ice, some part over here may become lesser than 4 degrees Celsius. But if you have kept the thermometer sufficiently low, then that is the highest density water. So there the temperature is going to be 4 degrees Celsius. It's not going to be low. A little bit here, maybe it will go down. I didn't think of it so much. So again, if you place the thermometer higher up, then you're probably going to see some drop in temperature there. If it really way down, maybe it's going to be even more steady. Yeah. Over here, yeah, if you continue cooling it, yes, of course. If you continue cooling it, when this part has also turned into ice, then eventually it will spread and the whole thing will also solidify. And then the volume will expand, so you will find some ice sticking out from the top. If you left it open, if you have completely sealed it, it will crack the container. Okay, so what is the, in terms of application, just directly, any of you who have put ice trays inside the refrigerator, right? And I mean, you were thinking of using it the following day, but let's say the same evening you had to take it out because there was a hot day, you wanted to cool something down. Have you noticed that the top part of it is ice, and then inside you can actually see the water? So if you kind of try to take it out, you see that it's like hollow inside because all the water has come out. So the top part of it is, so the top part of it freezes. The inside part of it remains, the lower part of it remains at 4 degrees Celsius. That's because of anomalous expansion. Okay, in cold countries, when you have a water body, right? You have a water body and it's liquid. And the external temperature starts to drop. So it's gone to something like -5 degrees Celsius. Maybe it has to go lower. I don't know. I live in tropical regions, so I've got no idea about this. So then what happens is you're having heat energy escape from this, right? So the temperature of it will start to drop. So when the temperature reaches 4 degrees Celsius, maximum density is achieved. So the warmer water will, the higher density water will settle down at the bottom. Okay? Then the top part of it will continue to lose energy. And then what will happen is the upper crust will actually get converted into solid ice. Depending on how cold it is. The thickness depends on how cold and for how long it has been cold. But they find that sometimes you even have aquatic life surviving under the. Try to draw a fish, maybe even some plants. These plants and the fish won't survive if the water freezes. They die. But since the temperature over here is at a nice 4 degrees Celsius, we die at 4 degrees Celsius for sure. But some aquatic animals and plants can survive. Even though at the top, people might be ice cream. So that's another consequence or phenomenon associated with this anomalous expansion. So the point being, I hope it's now clear how the Hope's apparatus or the Hope's experiment uh, demonstrates that anomalous expansion of water is indeed true. Any questions?